Hello and welcome back to another video for IGCSE Physics. In this video, we'll discuss some key graphs. Remember, whenever you're solving graphs, always use a sharp pencil. Cover more than 50% of the graph. If your graph is too small, you might lose mark. Finally, always label your axis with units. When you're labeling, for example, if you write time, never forget to write the unit, for example, seconds. And sometimes you will have some graphs which may look like this, and you might have time per hour and distance. For example, if you're asked to find speed in kilometer per hour, meter per second, you might have to convert the units. A lot of people don't pay attention to the units and lose a lot of marks. So these are some small mistakes that can be easily avoided. Now let's look at the distance time graph first of all. So here we have time on x-axis, distance on y-axis. Now I have made another video where I discuss these graphs in detail. I have linked that in the description. But on we can see that A to B is a straight line, so this is speed. Gradient of a distance time graph represent speed. So A to B we have constant speed, B to C the object is stationary. C to D there is a curve. Curve means that the speed is changing, so it means that it's accelerating. How do you know this is accelerating or decelerating? Because the gradient is becoming more. The graph is becoming more and more steeper. If it's becoming steeper, that means your speed is increasing. And then finally, we're going down, so we have constant speed. But the difference between A to B and D to E is, from D to E, we're moving back to the original source. When we reached E, we are back to the starting point. Now, one more thing that you can notice here, that we have a curve, okay? And if they ask you to find the instantaneous speed of that point, you have to draw a tangent and then find the gradient of that tangent. Now, speed time graph, similar idea. Gradient represents acceleration, and area under the graph represents distance traveled. A to B, we have constant acceleration. B to C, we have a changing acceleration. Now the curve is becoming less and less steeper, so the acceleration is reducing. C to D, no, zero acceleration, constant speed. And finally, D to E, we have deceleration. Now, if you have two graphs like this, here and something like this. So we have acceleration on both of these regions. But we can say acceleration is going to be higher in this region compared to this. Why? Because the graph is more steeper. Now, if you see a distance time graph, and if you see a curve on that time on the graph, it means that the speed is changing, so it's accelerating. In the first half, the graph is becoming steeper, so that's acceleration. Second half, that is deceleration. Now we have a graph that shows time and velocity, and we can see that this is a graph of a tennis ball and a beach ball that have reached terminal velocity. Can you identify which one? Now, terminal velocity is the velocity of a falling object where the acceleration is zero, resultant force is zero, and it's moving at a constant velocity. The upward downward force of the weight is balanced with the upward force of the air resistance or drag. It depends on two things. A, it depends on the mass of the object. If there is more mass, there is going to be more terminal velocity. It also depends on surface area. If surface area is higher, terminal velocity will be low. So you can see we have a tennis ball. It is small and dense, so this would be the graph. It has a higher terminal velocity, and it reaches terminal velocity later compared to the beach ball. This is for the beach ball. The terminal velocity is lower for the beach ball. Now we have some other graphs. Here we have a force distance graph. So on x-axis we have distance, and on y-axis we have force. Now, if you're asked to identify the area under the graph, but you don't know what quantity will you get if you find the area of this graph. To do that, remember this tip. To find the quantity that you will get when you find area under the graph, see what is the quantity of y and x-axis and multiply them. So for us, it's going to be force in y-axis times distance. Now, what is force multiplied by distance? That is work done. W equals to FD. So in this graph, area under the graph represents work. Notice that this can be applied to any graph, even to this speed time graph. Okay. If you see area under the graph is distance, because distance equals to speed multiplied by time. On the other hand, if you want to identify the quantity when you find the gradient, if you divide the quantity on y-axis and the quantity on x-axis, what do you get? For example, in this one, you have, let's say, a graph of like this. You have a graph of work done on y and force on x. You're supposed to find the gradient. Now, gradient is going to be work done over force. Remember this equation, work equals to distance divided by force. So work divided by force will give you distance. So here the gradient represents the distance traveled. Okay. Now, if you have energy time graph, let's say, for example, something like this. What does the gradient represent? Here, in this graph, we have y is energy and x-axis is time. So energy over time equals to power. Therefore, in this graph, gradient represents the power. So if you don't remember what can we find with area under the graph and the gradient, just remember this hack. Gradient is going to be quantity of y over x, and area is going to be quantity of y multiplied by x. Now, here we have again a force versus extension graph. This is for springs or other objects, which, for example, an elastic band. Now you can see that here, as the force is increasing, the extension is going to be increased. Like this, it obeys Hooke's law because a straight line passing through origin. Remember, this region is called the elastic region until it reaches E. This point is the limit of proportionality. After that, it does not obey Hooke's law anymore. This region is called as plastic region. For example, here it might have been deformed, and here maybe the spring broke, right? So now again, if you're asked to find the gradient, what is gradient here? Stretching force divided by x-axis, we have extension. Now remember the formula, k equals to f divided by x. So we get k, we get the spring constant. The gradient here represents the spring constant. Alright, now we have something called analog and digital signals. In analog, we have a whole variety of values, right, which changes. Now, let's say if you're asked to convert this into a digital signal. How is it? It's actually very simple. Remember, digital signal has only two values, 0 or 1, or yes or no. It has two values. So what they do is that in analog signals, they decide that, okay, we'll decide, for example, 2 as a threshold. Any value below this number is going to be 0. Any value above this number is going to be 1. So let's try to draw the graph. This is 1. So we can see from the region between 0 to 10, our values are greater than 2, right? We have a positive value like this. What about between regions 1 and 2? Now 1 and 2, obviously they all fall below the threshold, so it's going to be 0. It remains like this. What about between 2 and 3? Again, this is below the threshold, so that is also going to be 0 here. What about in 3 to 4? This value is greater than threshold, so our value would be 1 this way. And that's our digital graph. We only have either yes or no, either 0 or 1. Okay, now we can move on to electricity. So in this graph, we have current on the x-axis and voltage on the y-axis. Sometimes they can even reverse this. Okay, so make sure to look at what are on the axis. Now this represents an ohmic conductor, for example, a resistor. It obeys Ohm's law because the line is passing straight through the origin. What does the gradient represent in this line? So gradient is y. What is in the y-axis? We have voltage divided by current. If you look at this equation, voltage divided by current represents resistance. So in this graph, gradient represents resistance. Notice if this was reversed, the gradient would not represent resistance. It might represent 1 over resistance. So take care of that. here we have current on the y-axis and voltage on the x-axis for all of them. Okay, so if you have a filament lamp, it obeys Ohm's law until a certain point and then it curves. Semiconductor diode, it's 0 on one side and then it increases on the other side. Thermistor, resistance depending on temperature, it's also a curve, it's not straight line. Now we have DC and AC. Remember what is DC? DC is direct current. This is the symbol for DC. So we have on x-axis we have time, on y-axis we have the current. When there's a straight line, this is a steady DC. Whenever you have these different curves, this is a varying DC. It is not stable with time. On the other hand, we have something called an AC current, AC graph. The symbol for AC power supply is something like this. We have this in between. Now you can see the current varies between positive and negative, negative. In one cycle, we have a positive and a negative. This is one cycle. And in another cycle, we have another positive and negative, and it's just repeated over and over. What happens if we attach a diode? Remember, diode is supposed to rectify the current. It only allows the current to flow in one direction. Here to here, the current will be positive. And then in this region, the current will remain 0. And then again, in this region, we have a cycle again. And then finally, 0 again. This is the purpose of diode. Diode converts AC into DC. Because DC is direct current only flows in one direction in DC. Okay, now we have two curves. We have a heating curve and a cooling curve. In heating curve, look, we're applying heat to the substance. As the time is increasing, the temperature increases until there is a change of state. So solid is turning into liquid and melting occurs. Now at that time, even though the heat is being absorbed by the material, the temperature is not increasing. So this is used to increase the potential energy. Remember, here kinetic energy is increasing. Here in melting, potential energy is increasing. Now, after all the substance has melted, the temperature will start increasing again as a liquid. So kinetic energy is increasing. Remember, when temperature is increasing, kinetic energy is increasing. When the state is changing, potential energy is changing. So when it reaches 100, this is for water, it boils, all of it is boiling. So the potential energy is changing at this point. And then it has turned into gas. When all the particles turn into the gas, temperature starts increasing. This is used to increase the kinetic energy. So kinetic energy is for changes when temperature changes, and potential energy changes when the state changes. On the other hand, we have a cooling curve. This rule for energy change applies here as well. Let's look at what happens to our gas when we are cooling it. Gas condenses. When all of it condenses, it turns into liquid. The temperature falls again until 0. At this time, liquid starts freezing. When it has frozen, it turns into solid and the temperature starts reducing again. So that is a cooling curve. Now we can move on to something else. I saw this in chapter 2.2, thermal properties of the book. So this represents the unusual expansion of water. What does this mean? So for example, here on the x-axis, we have our temperature. On the y-axis, we have our volume. As the temperature is reducing, what happens is that obviously it's contracting, as it should, because temperature is reducing, the molecules are coming closer to each other, so it's becoming smaller and smaller. But the thing is, after 4 degrees Celsius, it changes. Instead of, even though the temperature is reducing, it starts expanding. This is unusual because it only happens with water molecules. It doesn't happen with other substances. So at 4 degrees Celsius, you have the maximum density, and it has contracted as much as it can, and then it starts expanding. Now, why does it happen with water molecule? It's because it forms some bonds, and those bonds start to break at this point. And when those bonds break, water molecules are free and they expand. Okay, until 0. So It contracted until 4 degree. From 4 to 0, it expanded. And then when it reached 0 degrees, remember at 0 degrees, it starts freezing, right? So the temperature remains same as we mentioned before. When it's freezing, the temperature does not change at 0 degree. So the temperature remains same, but the volume increases a lot. And then after that, all of it has turned into ice. And then when the temperature reduces even more, it contracts. So this is the volume temperature graph just for water. Okay. Moving on. Now we have Celsius and Kelvin scales. This is very simple. The temperature in Kelvin equals to 273 plus theta. Theta is the temperature in Celsius. Now we have temperature on the x-axis and volume on the y-axis. At this point where we have negative 273 degrees Celsius, or we have 0 Kelvin. At this is the lowest possible temperature, or is also called the absolute zero. It's on the Kelvin scale, it's 0 Kelvin, okay? At this point, particles have zero internal energy. They have no kinetic energy, they have no potential energy. Temperature cannot fall below this. So this is negative 273. But on the other hand, if this is 0 Kelvin, but at 0 degrees Celsius, we start from here. Why? Because there is some kinetic energy and potential energy, and there is some volume. So we cannot start from here. This at 0 degrees Celsius, the temperature is 273 degree Kelvins. Now this graph is just for water, and this graph is for all the other materials. Next point, we have waves. So remember, a wave looks something like this. This is one cycle of the wave. A wave is made up of a crest, which is positive, and a trough. Another positive and negative forms another cycle of the wave. The length from here, from the undisturbed position to the maximum point, represents the amplitude. This is also the amplitude. On the other hand, the distance from the starting point to this represents the wavelength, okay? This is also the wavelength. Wavelength is represented by lambda. Now, if we start from here, we have one trough, one crest. So this distance, this one, that also represents the wavelength. Wavelength is starting from one position to another, to the next similar position. For example, here, the crest to crest, that is also wavelength. And what is frequency? Frequency is the number of complete waves that you can form in 1 second. So if they ask you to draw the graph for a sound wave which is louder, the amplitude will be greater. So let's say if this was the original wave, how will you draw a sound which is louder? It should have a greater amplitude, but the wavelength is same. Now if they ask you to draw a higher pitch sound, so in high pitch, the difference is that we'll have more frequency. So let's say if this was the original one, the amplitude will remain same, but the frequency will be greater. And if frequency is greater, that means wavelength is smaller, like this. Same amplitude, but more frequency. Now our last topic for today is half-life. Half-life is basically the time it takes for half of the radioactive nuclei in a sample to decay. So that means here we had 80. When it reduced to half, for example, here it's 40. Let's try to see the time for it. That is 10. So after 10 minutes, we have half the number of atoms. Therefore, this is the half-life for this substance. Now let's see another one. So 40 becomes half. This is going to be, let's see the time for that. That's 20. So 20 minus 10 is also 10. So we have 10 minutes. Again, if you repeat that for 10, you get 30. 30 minus 20 is 10. So every 10 minutes, the atoms are becoming half. Half-life is 10 minutes. Remember, for one radioactive isotope, it's same. Because you notice from 80 to 40, it takes 10 minutes. From 40 to 20, it again takes 10 minutes. From 10 to 20, again takes 10 minutes. So it's constant for one isotope. It can be, for example, for this one it's 10 minutes, but it can change from millisecond to as much as billions of years. It's different for every substance. So after every half-life, for example, after this much time, half of the radioactive material has decayed. Here we have an example. For example, if half-life is 20 years, what fraction of material is left after 60 years? So for example, initially, at time 0, fraction was 1, like full number. Now after 20 years, what happened? It became half. After that's one half-life, it became half. After 40 years, it became half again. So half divided by 2, this is going to be 1/4 of the original sample. After 60, another half-life, so 40 plus 20 is 60, is going to be 1/4 divided by 2. It becomes 1/8. So after 60 years, that is after 1, 2, 3 half-lives, you are left with 1/8 of the original material. I hope this video helped you. If it did, make sure to give it a like and share it with your friends.